Hi everyone, welcome to my channel. I'm Idriss and this is Ship It with Idriss, where we implement production AI from first principles. So a little bit of context before we get started. I'm a senior engineer and I spent the last few years building production LLM platforms, retrieval systems, agentic orchestration, and validation frameworks that serve thousands of engineers at production scale. So the thing is, most of what I learned from building, and not really from tutorials or lectures, but from shipping code and observing its performance in production. But I realized that most of that experience I never shared publicly, so this channel is me fixing that. Every week, I'm going to take an AI engineering concept and build it 3 ways: brute force, optimized, and AI assisted. So there'll be no slides, minimal theory, but mainly just code. So this is episode 1. So let's get started. So for the first series, we're going to focus on RAG, Retrieval Augmented Generation. If you haven't come across this before, it's pretty simple. Large language models are trained on public data, which means that they have no insight into your company's internal documents or your specific knowledge base. You can do other techniques like fine-tuning, but they can be expensive, slow, and it's really hard to keep it current. So instead of doing that, you can get the relevant documents at query time and then add it to the prompt along with the user's query, send it to the LLM, and then the LLM's responses can be grounded within the context that you've provided there. This is likely the most dominant pattern in enterprise AI right now. So if you're building a chatbot that answers questions based on internal documents, you're likely using RAG. This is how you make the LLM useful in an enterprise setting. So this series is going to be split into 3 bite-sized videos and maybe a 4th video, a special bonus video if we have enough time. And the code will be committed to my repository and you should be able to find a link to that down below. But here we actually have a quick example. So for example, you've likely seen something like that. A customer comes in, asks a question like, what is the refund policy for enterprise customers? That question gets embedded and some kind of similarity search or other technique gets used to retrieve or find similar chunks or chunks that are relevant. So these would be the relevant chunks that it's pulled from the vector store, and the top results will get attached to the prompt along with the user's question. So the question plus the prompt sent to the LLM, and the LLM is now able to answer that domain specific question grounded within the context that was provided. Okay, so we're here in my IDE. I have some notes on the side. I'm using Visual Studio Code for Windows. Feel free to download Visual Studio Code for free from the website. I've got Python 3.13 and I've created a virtual environment for this project. So if you need to get to this point, you can find some other tutorials that will get you to this point, but our goal is text retrieval. We have this folder here with some sample documents that were randomly generated. So step 1 will be to load the documents folder. Step 2 will be to break them down into chunks using fixed size character splitting. Step 3 will be turn each chunk into numerical vectors using TF-IDF implemented from scratch. TF-IDF is term frequency inverse document frequency, which is a way of scoring how important a word is to a specific chunk. If the word appears often in one chunk but rarely across all chunks, it gets a high score. If it appears everywhere, words like the or is, it gets a low score. It's simple. It's been around since the 70s and it's still the baseline for more advanced methods. And then step 4, we're going to compare vectors using cosine similarity, also from scratch. And step 5, build a query function that scores every chunk and returns the best matches. Okay, so this is going to be done in 4 steps. Let me create a new file here. Not in here, but in here. And we will call this BruteForceRAG.py. And up here, we are going to add a doc string with our steps so we don't get confused. Step 1, we are going to load the documents from the specified directory. Step 2, we are going to break it down into chunks. Step 3, we are going to turn each chunk into a numerical vector. Okay, step 4, compare vectors using cosine similarity. And then step 5, build a query function that scores every chunk and returns the best matches. Okay, so let's start with importing some, actually we'll write the functions and we'll import as we go. So the first function will be load documents, def load documents. Okay, so we're going to load a specific directory from the path, and this is going to be a string input, and we are going to get all the .txt files in that directory, load the contents, and save them save the name and the contents in a dictionary. So our output is going to be, a list of dictionary string str, and let me actually do the doc string here. So load documents from specific directory and return a list of dictionaries containing the document's name and content. Let's keep that, and then here we'll do doc equals an empty list, and then we'll go for file name in os.list dir. So we're gonna list all the file names in this directory, folder path, and we're using OS to do that. So let's go up here and import OS. Okay, right. Then we'll go if file name dot ends with .txt. So we're only targeting text files. So then we'll go with open os.path.join folder path, comma file name. So we're doing this here just so we can get the full path, and then we're going to read that in. So like this, I could do this on separate lines, but I'm just going to do it as one, as f, so as file. Okay, and then the content, so that's loaded as f. So the content within that document is going to be content equals f.read. So we're going to read the contents, so that will come out as a string, and then we're going to append the name and the content to our doc, and that will be a list of dictionary strings. So doc.append name, file name, content, content. Okay, and then once we're done, we will return doc. Okay, so like we said, we're going to input a folder path into this function. We're going to initialize an empty list for all the documents, and then we're going to get each file name in this path, we're going to traverse through each file name in this path, and if the file name ends in .txt, so we're only targeting text files, we're going to open that using the full path, and we're going to join the folder path with the file name to get the full path. We're going to read that and store it in F, and then the content we're going to read from that document, and that's going to be string, and it will be saved in content, and then we will append this document, the name, which is the file name, and the content to doc. Actually, let me make this a little safer and add an encoding in here. So encoding equals UTF-8. So next, these documents as they come out, right now they're still pretty large, but you could have documents with hundreds of thousands of lines of sentences or paragraphs and so on. So they're usually too large to just directly put in as chunks and retrieve, and likely the entire document isn't going to be relevant to each user specific query. So this is where we break them down into smaller sizes called chunks. And for this demo, we're just going to use the simplest chunking strategy. So split them into chunks of 500 characters. But what you'll see is that this method doesn't care if it's mid-paragraph or even mid-word. It will just stop at 500, and we'll see why this causes big problems later on. So df, let's call this chunk text, and we'll say text as a string, chunk size as an int, and we're going to make that 500, and we will output a list of strings. Okay, so we'll once again initialize an empty list for the chunks. Chunks equals an empty list, and then we'll say for I in range. So we'll go from 0 to the entire length of the text or the document that's input, and the step will be the chunk size that we specify. And what you'll see here is that, let me just fix chunk size. What you'll see here is that when you run this, you can actually overwrite this default 500. So if I was to make this bigger or smaller, I can just overwrite that when I'm calling the function, because I'm using this variable here. Okay, so now we'll say chunk.append, or should I say chunks.append text I plus chunk size. So right now we're extracting from index I. So I is going to start at 0, and then I plus chunk size, so that's 0 plus 500. So the first time this goes around, it's going to take the first 500 characters and put them into a single chunk. And the next time, I is going to start at 500, and so on. So after we've done that, all we have to do is return chunks. So this is simple enough. Return chunks. Okay. So next we need to turn the text into numbers, because we can't do math on strings, and we're going to build a term frequency inverse document frequency from scratch, and this is going to be able to tell us or answer the question of how important is this word in this chunk compared to all other chunks. And we're going to start that by creating a function called tokenize or tokenizer, which is going to lowercase everything, strip all the punctuations, and split on spaces and drop single character tokens. So let's call this tokenize. Nice. And the input is going to be text, and that's going to be a string, and the output is once again going to be a list. of strings. So first we're going to lowercase everything, because if we don't, then you might have tokenize with a capital T and tokenize with a lowercase t, and they will be seen as different words. So text.lower, and then we will say, actually, yeah, so we'll say for character in, I think I have something over here. Okay, so now I'm going to replace common punctuations. This isn't exhaustive, so I might have left something out, but I'm going to use this set right here. You can feel free to modify that as you wish. And what we're going to do is text equals text dot replace character with a space. So essentially we want to remove all of these punctuations, as once again they will you know, give us different words for the same word. So if tokenize with a full stop at the end is going to be seen as a different word to tokenize without full stop. So now we'll return, so let's just say return word for word in text dot split. So we're going to split this text by space if length of the word is greater than a single character. Okay, now we're going to build our term frequency. So we'll say term frequency term. So what this function is going to do is see how often a word appears in a chunk, and this is done by number of occurrences divided by the tokens in that chunk. So for example, if the word frequency was to appear 3 times out of 100, then the term frequency would be 0.03 for that. So term, which is going to be a string, and then document tokens, which will be a list of strings, and then our output is going to be a float. Okay, so we'll say if not document tokens, then we are going to return a result of 0 as a float. And then we're going to count, the count will equal to document tokens dot count, and we'll count the term that we're looking for, see how many times it shows up, and we will return the count divided by the length of the document tokens to get our term frequency. Next, we want to do our inverse document frequency. So we'll do inverse document frequency. So this is a bit of the smarter bit where, you know, just because, so for instance, if a word appears in every single document or every single chunk, it's not really going to be useful. So common words like is or the aren't really going to be relevant to, aren't really going to be relevant to any query, you could say. So what this does is if a word appears in too many chunks, it gets penalized, and words that appear in very few chunks get boosted. So for this, we're going to do term, which is going to be a string. It's going to be similar. So we'll say corpus token or something. And that's going to be a list of strings, and my bad. and that is the output. Once again, is going to be a float. Okay, and for this, I think we are going to have to import math. So num.docs equals len corpus tokens, and then docs containing. So the docs containing the term is going to be the sum of 1 for tokens, or for, let's say, for doc in corpus tokens if term in doc. Okay, and then if docs containing equals 0, also going to return nors 0 because it has no inverse document frequency. 0.0 as a float. Otherwise, so we are going to have to import math here. So import math, and then otherwise we will return math.log num docs divided by docs containing. Okay. So essentially that's the total chunks divided by the chunks containing this term that we're returning here. Okay. Okay, so we have got a function to split our documents into chunks of 500. We've got a function that will split each chunk into tokens. So that's individual words as long as it's greater than 1. And we have a function that will determine how frequently a term, so like a word, shows up in a specific document. And we also have another function here, which is the inverse document frequency, which will determine how frequently a term shows up in all documents and penalize it if it appears too many times using this function. Also boost it if it only appears a few times. So now what we're going to do is we're going to build a vocabulary, which is going to be every unique term in our entire document collection. So it will be our global vocabulary, and then we can get our term frequency, inverse document frequency vectors out of that, which will be numerical and allow us to compare them using similarity search. So we'll go with def build vocab. And actually, just for anyone who's getting confused by the document tokens, the document tokens are essentially the words here. So each of the words here, and the corpus tokens are each chunk. So here we are comparing how frequently a word appears in a chunk, and here we are checking out how frequently a word appears in all chunks. So vocabulary. So the input will be corpus tokens, and our output is going to be a list of list strings. Oh, sorry. The input will be a list of the strings, and our output will be a list string. Okay. So we'll create a set to ensure everything is unique. So we're only going to have each term in here once. And then we'll do for doc token tokens in corpus tokens vocab dot update. So we're going to update doc tokens. So we're going to update vocab with the tokens in each document or each chunk, and because this is a set, each one will only appear once in vocab. and then we can sort them and return them. So return sorted vocab. Okay, so that's our full vocabulary, and now we can go on and build our term frequency, inverse document frequency function. So let's just say term frequency, inverse document frequency. All right, and actually we'll say vector, yeah, because the output will be a vector. And the inputs, we're gonna get our documents tokens, our list, which will be a list of strings, and then we will have our corpus tokens, which is a list of list strings, and our vocabulary. And the output will be a vector, so a list of floats. And so we'll initialize our empty vector. And now what we're going to do is go through every term in vocabulary. For a term in vocabulary, we're going to get our term frequency for each term and our inverse document frequency. So term frequency equals, so this is where we're using our functions we created earlier, and we're going to have our term and our document tokens going in here, and then our inverse document frequency, we're going to have use that inverse document frequency function, and here we'll have our term and our corpus tokens. Okay, and then to compute our vector, we're just going to multiply the two. So that'll be, so we're going to append to our value, so append for that term, so term frequency multiplied by inverse document frequency. So that'll be our TF-IDF for that specific term, and we'll append it to that vector, and then we are going to return that vector. So this gives us a vector for every single term in our vocabulary that was built off the documents that we are going to be working with. So now we're going to build our cosine similarity. So we have our vectors, and now we need a way to compare our vectors. So essentially comparing each term in the user's query against the terms in our vocabulary of vectors. And essentially this just measures the differences in angle between two vectors. So if you have a vector, so for instance, if they're in the same direction, you'll get a result of 1, which means that they're identical matches. And if it's perpendicular, then you'll get a value of 0, which means it's completely unrelated. And this is actually the same method that most vector databases use, including Pinecone, Weaviate, Quadrant, and many others. So let's start with our function, cosine similarity t, and we'll have vec a, which is a list float, and vec b, which is a list float, and our output, which will be a float. So to compute this, we will get the dot product and divide that by the magnitude. So dot product equals sum of a times b for a comma b in zip vec A, comma, vec B. And then we'll get our magnitude of A, which equals the square root. So we're going to use math for this. Root of the sum of A for A in vec A. It's telling me I have an error somewhere here. Let me see. Okay. And then magnitude B equals math, the square root, sum B power of 2 for B in vec B. And so if magnitude A equals 0 or magnitude B equals 0. So if they're completely unrelated, we just return float 0 for that because it's not related. Otherwise we'll return so it's dot product divided by magnitude of A and multiplied by magnitude of B. Okay, so now we have a way to compare the terms from our query to the terms in our chunks. Okay, so let's tie this all together. So I'll create a class where the constructor will load the documents, chunk them, and then we'll tokenize every chunk. We'll build a vocabulary and we'll pre-compute the term frequency, inverse document frequency for every chunk. Then we'll have a query method and that will take every question, compute a term frequency, inverse document frequency vector, and then we can compare the question against every chunk using cosine similarity. So that is essentially the brute force approach. So let me start this function here. So actually class, I'll say brute force RAG, and we will have an init self folder path string, and then chunk size. We want to define that in the init. Chunk size, which will be an int, and we're going to do 500. And then self dot docs will equal load documents, and for the given folder path. Self dot chunks will actually this will be a list of strings, and we'll initialize that as an empty list. And then we can do for doc in self dot docs self dot chunks dot extend chunk text doc content chunk size. Okay, so we are loading our documents. initializing an empty list for chunks, and then with our loaded documents, remember this outputs a dictionary, so we will have the document content and the file name. So we're actually going to chunk the content by the defined chunk size, which will be default to 500. So next we're going to do the tokenization. So self.corpus tokens equals tokenize chunk for chunk in self.chunks. Okay, and then we will build our vocabulary. Self.vocabulary equals build vocabulary, and we'll use our corpus for that. Self.corpus tokens. Okay, and then we need our vectors. So self.vectors equals our term frequency inverse document frequency vector, and we'll input in here tokens, self.corpus token, self.vocabulary, and this will be 4 tokens in self.corpus tokens. Okay, so that should give us all of our vectors, and now we're ready to build our query function. So df query self, we could say question string top. Okay, so we're only gonna return the top 3 most relevant chunks, so that'll be an int. We'll default it to 3 at least, but these can be parameters that can be tuned by whoever is going to be serving this, and the output will be a list of tuples, string float. Okay, that will allow us to see the similarity scores. Oh yeah, sorry, that's correct. So we'll do question tokens. So we need to tokenize the input or the question. So tokenize question, and then vectorize it. Question vector equals term frequency inverse document frequency using our vocabulary. So vector question tokens self.corpus tokens and self.vocabulary. So we had to tokenize this so that we can get a vector that matches the vectors in our data collection. So now we will get a vector for this, and then we can do similarity score. So do a scores, we'll initialize empty scores, so like this, and then we'll do for I chunk vector in enumerate self.vectors. Score will be our cosine similarity, and this will be our question vector and our chunk vector, and then we'll append that to the score. So scores dot append self dot chunks I and score. Okay, so we'll get the similarity and then we'll append that to scores. So next, we can sort them descending so we can get our top K. So we'll do scores dot sort key equals, we need the lambda function for this, x x1, and because we want it descending we have to do reverse equal to true. Okay, and then we can return scores, but we're only going to return the top K, which is going to be top K. Okay, so now we should have everything ready to test this. Okay, so now it's time to actually try and test what we've created here. So if name equals main, this isn't mandatory, but essentially if you only want to run this when this is your main file, then we just add that if name equals main for safety. So we'll initialize the RAG. So let's say RAG equals our brute force approach. Brute force RAG, and this will be a string of our data directory. But actually I need to do data directory equals data sample docs. Hopefully that's good. So for our data directory, and then let's do our query. So query 1, we can say what is retrieve, we'll add some upper and lowercase, so retrieval augmented generation, and we'll add some punctuation, and then we'll have query 2 how do you make sure AI doesn't make things up? Okay, how do you make sure AI doesn't make things up? And then query 3 can be BM25 keyword search algorithm. So here's a couple of example queries. So what is retrieval augmented generation? How do you make sure AI doesn't make things up? And BM25 keyword search algorithm. So these should all be contained in here. So LLM hallucinations. So understanding and detecting hallucinations in large language models. So we'll see how this performs on our set. Everything in those questions should be covered in our documents. Okay, so now that we've done that, actually let's do this one by one. So do here results 1 equals rag.query 1, and then we'll do for I in, for I chunk score in enumerate results 1 print result I plus 1 score is score. This will be a float, so we'll format it dot for f, and we will do the first 100 chunks, maybe not 200 chunk. Actually we'll do 200. That's fine. Okay, let's close this off. Okay, now we're going to do the same for the rest of these. Oh, my bad. First 200 chunks. And I also, well, it's not that big a deal, but I should have closed that off. Okay. So now for the second one, we are just going to be lazy for the rest of this now. And we'll use completions. So the same, we are going to print the results for query 1, 2, and 3. Actually, to make this a little clearer, I am going to add something to the start here. So we can say query 1 results, because we're going to get multiple results for each of these. Then once again, we can do query 2 results and query 3 results. And actually, I will also print the query. So we'll do that for each of these. The same down here. Okay, so let's run this. Looks like my output got truncated. Let me run that again. Okay, so for our first, what is retrieval augmented generation? Text chunking strategies for retrieval augmented generation. So what we see here is that because this is keyword matching, I assume words like is and maybe what are going to get penalized heavily. Punctuations like the question mark are also going to be dropped, and we can see that there is a good match for retrieval augmented generation, which is why it was the top score. It scored higher than the other two, so because of that it was returned first. And we can see text chunking strategies for retrieval augmented generation. Chunking is the process of breaking large documents into smaller, meaning manageable pieces that can be individually embedded and retrieved. We can see that this is pretty relevant. Let's look at the second one, retrieval augmented generation. Once again, those words were caught. And then the third one, a much lower score, less than half of the first one. Evaluation metrics for RAG, measuring retrieval and generation. So we've got two words in here, two word matches. We don't have augmented, and that's probably why it scored lower, but we can see from the context that most of what it retrieved was pretty relevant. We're only returning the first 200 characters here, so it's truncated. However, let's say if I looked at, actually all of these seem to be starting from somewhere sensible. Evaluation metrics for RAG systems, retrieval augmented generation, and text chunking. Okay, let's look at question 2. So how do you make sure AI doesn't make up things? So the score is, for the first one, relevant to the query. So it looks like we're starting in the middle here. Relevant to the query. So what happens when you take the 500 tokens is it's going to stop at an exact point and then start the next chunk at that point. So here we've got the tail end of a sentence. So this is where we can use other techniques like add some overlap to each chunk, so each chunk has an overlap of its previous chunk and of the next chunk, so it's more likely that you'll get more context and things won't be truncated. And generally chunk sizes would maybe on average 6,000 tokens, and you might do 1,000 token overlap on each side. You would generally play around with this a little bit until you get something that feels right for your particular solution. And then there's more advanced techniques like semantic chunking, where it keeps everything inside a chunk should be relevant to a specific context. And people have found a lot better results with that. But let's look at this. This is just keyword matching. How do I make sure AI doesn't make things up? So for instance, how do I make sure all of these could be penalized for occurring too many times? AI might get boosted, but there's not too many strong words in this for straight keyword matching. And if we look at what was returned, we don't see, let's see, relevant to the system. Tells you how much. Okay, so if we look at this, it really doesn't tell us how to make sure that the AI doesn't make things up or doesn't quote unquote hallucinate. If we had the word hallucinate in the query, if we look at the sample data, we have LLM hallucinations. Let me pull this down. If we use the word hallucinate, it would have picked up on things like this. So let me actually switch that and say, how do we make sure an LLM doesn't, and let's say, doesn't hallucinate, just like that. And let's run that. Actually, now that I think about it, I don't think hallucinate was in here. So we want the word hallucination. So how do we, let's say, avoid hallucination in RAG systems? Something like that. So hallucination should get tagged. So if I run this again, what do we get? So for query 2, we've got a higher score, which is good. And I still do not see the word hallucinate in here for some reason. Faithful. This is interesting. And I might actually just reduce this. Let's get it to really trigger hallucination. So let's say how, or let's just say avoid hallucination, because we know that this word is really going to trigger. So let's run this. And see what we get. So for query 2, avoid hallucinations, score to 0.24. It's a very high score. Understand and detecting hallucinations. So now we see that's a trigger into correct context. Similarly for question 3, we have the, where is question 3? BM25. Once again, because this is a keyword search, we don't have this anywhere, as far as I'm aware, but let me just confirm. Search fee. So this isn't anywhere in any of our documents. So what this tells us is that keyword search is pretty weak. It's a great starting point, and it will show you the limitations of that technique and why there are so many other techniques that were required to be developed to make these systems more robust. So to wrap up, I guess what we did today is we built a complete text retrieval system from scratch. We did the document loading, term frequency, inverse document frequency. We made the library from our vocabulary, and then we created a cosine similarity method that we could compare users' questions against our document collection. And then we saw the limitations of term frequency, inverse document frequency, something created in the 70s that's still relevant today, but has its limitations.